Okay. I had a couple of brain glitches, had to redo all that, but it's simple enough. As we saw, this matrix, if we reduce it by subtracting 2 times the first row from the second, we get this upper triangular matrix. The elementary matrix that does that is the matrix that subtracts 2 times the first row from the second from the identity. And we saw that last time. So there it is. So that if we multiply the elementary matrix by A, we get this matrix. So that A is the inverse of the elementary matrix multiplied by this. It's multiplied both sides by the inverse of the elementary matrix. The inverse of the elementary matrix is a matrix that undoes this operation. This operation subtracts the second row from the first. You would undo that by, it subtracts 2 times the first row from the second, and then you undo that by adding 2 times the first row to the second. And you can see that if we add 2 times this row to this, we're going to get the 4 and the 5. Okay. We're going to add 2 times this to 0, which is 4. 2 times this is 2, added to 3 is 5. So there's the inverse of the elementary matrix. And we can verify that. If we multiply this matrix by this matrix, we do get the identity. So that A equals 1, 0, 2, 1 multiplied by 2, 1, 0, 3. Now, it's a fairly simple example. My book has examples of 3 by 3 matrices that we do this with, but that's the scheme. Now, as long as you can reduce the matrix A to upper triangular form just by adding multiples of rows to others, you're going to get an Lu decomposition. It's not always possible. It doesn't work for every matrix. But okay, there's a statement. If you reduce A to upper triangular form by adding multiples of rows to rows, then A can be expressed in Lu form. I'll mention that it doesn't hurt if you multiply a row by a constant, but it's not necessary to do that. You can always incorporate the constants. We're not trying to get ones in the diagonal, for example. Any Lu form works. So this is the most efficient way to accomplish. And looks like I've got a, no, I guess I've got it. Okay. Now, once you have the matrix in Lu form, what do? Let's say you have the equation AX equals B, typical matrix equation. That becomes LUX equals B. Okay. Well, what you do is, first thing you want to do is, there's no good way to do this. I mean, you could do Lu inverse, but then you'd have to invert both of these matrices, which for 2 by 2, that would be simple. But for larger matrices, that would involve a lot of computation. And one of the advantages of the Lu decomposition, the main advantage, is that it increases the efficiency of being able to solve an equation like this. Even though there are several steps, once you get the matrix reduced to this form, you get now two matrix equations that are easily solved. And let's see what that means. Okay, so here's your matrix equation. You get two equations. One equation would be Ly equals B, because L multiplied by this is B. So you can solve this equation very easily because, well, with the lower triangular matrix, it's easy to solve. Okay, we'll demonstrate that, and you'll see. But the matrix is already in a reduced form, so it's going to be very easy to solve. So you express this as Ly equals B, where Y equals UX. Then solve okay. You look at the process of Lu decomposition. Just first with a simple, in this case, let's say we have a simple example, and AX equals, you can verify this matrix multiplication. 3, -2. Of course, the 1, 0 row, two numbers, you're going to just select out the first row of this matrix, so we're going to get the 2, 1 down here. Then 2 times 2 is 4, is this original matrix. So we get 4. 2 times 1 is 2, 3 times 1 then is we can write 3. We add those, we get 5. So 1, this matrix 0, is 2, 1 form. Multiplied by 2, 1, 0, want to reduce this matrix, X equals 3, -2. I can, simply subtract 2 times the first row from the second. Okay, so we solve 1, 0, 2, 1, Y equals 3, -2. I mean, it'll look better. And it's straightforward to solve that, because what does this mean? Well, it means if your matrix is X1, X2, so it's going to be, that means X1 second row 3 minus 2 times 2X1 plus X2 equals -2. And that's going to go in the second row. Okay, I'm going to actually write that out, although it's, I think, somewhat easier since we've done decomposition. You'll see, we know what the inverse of this matrix is. This is the elementary matrix. Its inverse is this. Okay, so let's get this right. Second row inverse is the E matrix that we used here, so we can multiply this E matrix by the 3 in the second row. So we're going to have 2, 1 solution. But let's go ahead and write it out, because we want to remind ourselves that this all comes from a system of simultaneous equations. We get X1 equals 3. Do this. Okay, so it'll be 2X1 second row minus 2 times the first. It's going to give us 0, 3 -2. Well, we already have our solution for X1. We plug that in, and that's upper triangular. If we look at the elementary matrix, it does the second row times. So we get 6 minus plus 2 times 2 equals -2. Let's see what that matrix is, -8. Okay, so the identity matrix, so our solution is, if we do second row minus 2 times the first, our Y is 3 -8. 1, 0. And we can verify that. 2, 1. 1, 0 times 3 -8. You know, this is elementary matrix. And then 2, 1 times 3 -8. 2 times 3 is 6. So the elementary matrix, -8. 6 and -8 is -2. We can verify the solution. Multiplied by the original matrix, and let's call this matrix A. Equals 1, 0, -2. We could also have multiplied by 2, 1, 0, 3. That's a lower triangular matrix times an upper triangular matrix. Alternatively, y equals 1, 0, 2, 1, that this doesn't inverse agree with this times, okay, so that we conclude that 3, negative 2, LU form of a matrix, and the matrix A, this matrix isn't unique. In other words, A can be expressed this way in LU form. It can be expressed this way in LU form. So our E inverse times 3, negative 2, because right there we've got it. There's our E inverse. Of course, we just look at our E and see what E inverse is. So this equals 1, 0, negative 2, 1 times 3, negative 2, which equals, well, 1, 0 times 3, negative 2 is 3. And then negative 2 times 3 is negative 6. 1 times negative 2 is negative 2, so that gives us negative 8. So we didn't have to write out the simultaneous equations, but it's not a bad idea to do that so we see what's connected to what. Okay, so there's our solution for y. Now let's try to find x. Okay, so we've solved the equation. What do you multiply by 1, 0, 2, 1 in order to get 3, negative 2? Okay. Well, what we multiply by this to get 3, negative 2 is 2, 1, 0, 3 times x. You know, this isn't working out. I'm going to stop this recording for a minute. I'm not sure why I'm not getting this right, but I'm not. And hard to write on this board. Sorry, that's a bad looking 8, but hopefully you can read it. Okay, so we have this, and now we can solve this. Now, this is an easy matrix to invert, but it's not always going to be easy. The elementary matrix is always going to be easy to invert, so you can always do this. Okay. But let's go ahead and write this out as a set of simultaneous equations instead of inverting the matrix. Sometimes you'll want to invert the matrix, or we could write out the augmented matrix and reduce it. I'm going to just remind us that we are ultimately talking about here a system of simultaneous equations. So I'm going to write it out that way. 2x1 plus x2 equals 3, and 3x2 equals negative 8. And a very easy system to solve. Solve the last equation for negative 8 and then use back substitution to find x1. That's really ultimately all we're doing. So we have x2 is negative 8 over 3. We take that, substitute it up here, and that gives us the equation 2x1 minus 8/3 equals 3. So that arithmetic is simple enough, so I'll probably mess it up. But we add 8/3 to both sides. So we add 8/3 to 9/3, and we get 17/3, and then we divide by 2 and get 17/6. And there's our solution. So that we conclude that x equals 17/6, 3. Now we can verify that with our original matrix. The 2, 1, 4, 5 multiplied by this should give us 1. And I'm really writing a fraction there, so I use a fraction line here, which doesn't belong there, obviously. Okay, so let's see if that works. Keep my fingers crossed. 2 times 17/6 is 17/3. And 1 times 3 is 3, so something's wrong. Okay, obviously I made some kind of a mistake at some point. Wrote these equations down correctly. There's something wrong with my logic. Boy, I'm not having a good morning. I'm not. Yeah, I'm solving the y. So you get 3 negative 2 out of this. And I'm not getting anything. So let's see. 8/3. That's 9/3. We do get 17/3. We get 17/6. Anybody want to tell me what I'm doing wrong? Okay. I can check up here the 2, 1, 0, 3 multiplied by this doesn't give me 3. This is very simple. So obviously I made a mistake solving these equations. I'm a little surprised I made that simple a mistake because I was actually being careful. But let's just see what happens if we solve this equation by row reduction. Going to give us 3. Sorry, 1, negative 8/3, 2, 1, 3, 0 here. And then we subtract this row from this one. It's going to give us the same thing. Have I written this down correctly? Well, I'm solving this equation. I'm not going to get all hung up in the arithmetic here. Because if I'm not seeing it, I'm not going to see it. Very simple equation by back substitution. Not give me what it should, but it should. I'm not going to waste time doing this. So let's look at the process again. Donovan just joined us. And Donovan, I'm sorry, I was working this out. And I don't know when you came in, but you probably had to wait a little bit, and I do apologize. Okay, it didn't miss much. I've made a lot of mistakes here. I'll try to correct that in the next segment. But we're looking at Lu decomposition, just to give you the overview and give everybody an overview. So if we multiply this matrix, which is in lower triangular, upper triangular, lower triangular because nothing but zeros above the diagonal, upper triangular because there's nothing but zeros below the diagonal. We multiply that out, we get this, and there's our matrix A. Still not going to work. Okay. We can reduce this matrix to upper triangular form in one simple step, and you can always do that with just a 2x2 matrix. With larger matrices, there's more to it. But we reduce this to upper triangular form by subtracting 2 times the first row from the second. Now, if E, elementary matrix, is the matrix you get from the identity when you subtract 2 times the first row from the second, then E is 1, 0, negative 2, 1. And E times A can easily be verified. Multiply this by this will give you this. Okay, so this is the elementary matrix that accomplishes this row reduction. It follows then, if EA equals this, then A equals E inverse times the reduced matrix. Okay, we just multiply both sides here, in other words, by E inverse. E inverse is the matrix that undoes the elementary matrix. This matrix subtracts 2 times the first row from the second. So the inverse is going to add 2 times the first row to the second, and it's going to be this. And you can verify then that A equals E inverse times this. You just multiply this matrix by this, and you do get the matrix A. It follows then that A is E inverse times this. So A is, here's E inverse, here's this. Okay, if we can reduce a matrix, so this is lower triangular, upper triangular. We've reduced the matrix A to lower upper triangular form. In general, if you can reduce a matrix, any matrix A, and you can do a large matrix, if you can reduce this to upper triangular form by adding multiples of rows to rows, then A can be expressed in LU form. If you can't do the reduction without switching 2 rows, then all bets are off. It's probably not going to work. I think it's certainly not going to work. We can prove that, but we're not going to bother. Okay, this is the condition. You got to be able to reduce A to upper triangular form just by adding multiples of rows to rows. Once you can do that, then any matrix equation AX equals B can be expressed as LU times X equals B. By matrix associativity, of course, LU could be grouped this way. And this matrix, or this equation, has the form LY equals B, where Y equals UX. If we solve UX equals Y, well, if we solve, we do LY equals B where Y equals UX. Okay, then once we know Y, well, Y is UX, so now you have UX equals Y, and you can solve that for X. And then we demonstrated this in a very simple example that somehow I screwed up, but you can correct it, but you'll see the process very easily. So you have AX equals 3, negative 2. If you have AX equals 3, negative 2, those are just numbers that I picked out of my head. Then your lower triangular matrix is your, again, E inverse here. Okay, so here's your matrix A. Well, your matrix A is lower times upper. There's the matrix A expressed as lower times upper. That's an LUX equals a B. We solve the lower triangular matrix times Y equals this. And that's very simple, except something's haywire here. Anyhow, you solve this. I solved it by simply writing out the equations. We could have solved it in any of 3 ways at least. we could invert this matrix and multiply by this. And of course, this is an easy matrix to invert. If you're doing a 3 by 3 or 4 by 4 or a 50 by 50 matrix, it's going to be a little more difficult to invert this matrix. Yeah, there's a mistake I thought I could have made. I'm still looking for my mistake. Okay. And in fact, we know the inverse of this matrix is this. But rather than using that, we just wrote out the equations. X1 equals 3, 2x1 plus x2 equals -2. And we see that this equation is easy to solve by back substitution or by forward substitution in this case. X1 is 3, so we replace x1 by 3. And we get 2 times 3 plus x2 equals -2, so that x2 equals -8. It follows then that your y is 3, -8. Now we verified that using the inverse matrix here. So we wrote y equals the inverse Did I invert the wrong matrix? No, I didn't. Okay, y equals the inverse of this matrix times 3, -2. And the inverse of this matrix is the inverse of your E matrix that we had up here. In other words, if this is the E matrix, which it is here, and I actually wrote that down wrong. It doesn't matter because we're doing the inverse of this matrix. Let me erase that. So obviously, if we multiply this by the inverse of this matrix, we get this. This matrix is the E inverse matrix. So its inverse is the E matrix. And I wrote an E inverse here when I did this. It was incorrect. Okay, so we have this. And the inverse of this matrix then is this. And again, if we've done the Lu decomposition, we always know what the inverse matrix is. And in general, instead of writing out the equations, we're going to use that matrix because that's a very efficient way to calculate the y. Remember, y, again, is our UX matrix. Okay, so there's our y matrix. I'll remind us that y is UX in this scheme. So that UX equals 3, -8. U is the upper triangular matrix, 2, 1, 0, 3. And we solve this, and this is really, really simple to solve. But I solved it. I still don't see anything wrong with my solution, but something's haywire in my brain because this doesn't work. I multiply this by the 2, 1, I get 17/3 plus 3 equals 3, and that's clearly not true. So there's something just terribly wrong with my arithmetic here. Okay, well, we could solve by matrix reduction, but that gives us exactly the same steps. I get the same results because my brain is stuck on whatever mistake I made, and I can't seem to find it or get out of it, which is kind of pathetic, but that's okay. You can solve this equation. We could invert this matrix. I'm not going to go to that trouble. We could invert this matrix and multiply by this and get the solution, and get a solution that we can finally verify. Okay, well, according to my bad arithmetic, 17/6 should be a solution to this equation, AX equals 3, -2. It's not going to be. Because again, if I multiply this x by a, I'm going to get 2, 1 times the 3, -2 column, and it's not going to give me what it should, which would be 3 here. So I'm not going to go any further with that, but that is the system. And it's a little confusing to understand this part of the process. The rest of it's straightforward if you can do it right. Okay. So again, you have AX equals B. If A is in LU form, then this is what the equation looks like. If you let UX equal Y, you have an equation you can easily solve because this is a triangular matrix. L is a triangular matrix. You can solve it by forward substitution. And then Y equals UX. You can solve for X and use an upper triangular matrix, and you can solve that by backward substitution. So it's a very straightforward process. Okay, well, I apologize for the numerous errors. Never occurred to me that I couldn't do that accurately, but it should. So that's the process. And that process works for matrix of any size, and it's if you can get the Lu decomposition, it can be the most efficient way to solve an arbitrary large matrix equation. So we're going to look at powers of stochastic matrices. If A is this, then A squared is this. Straightforward calculation. I think I did that one right. And a little bit of confirmation is if you multiply two stochastic matrices, it's not hard to prove that you get a stochastic matrix. So we add these, we get 1. We add these, we get 1. This matrix is still stochastic. A squared times whatever your configuration vector is. If it's the population vector, 500 sane, 500 demented, that's fine. If it's a stock market thing, and incidentally, I did post the correction to the stock market thing. If you didn't get that, let me know. I think everybody got it. That was never mind. Just you can see it's a pretty straightforward model. Should be helpful with homework. Okay, A squared times your X vector. Directly gives a result after two transitions. Okay. Well, if I do if I square A squared, that's going to be this. And of course, this is the square of this matrix. And if you write out what this means, you could replace this matrix by this matrix times this matrix. And when you square it, you get this matrix times itself multiplied by this matrix times itself. It's going to have 4 of them. And that's not just by some rule of algebra. You kind of want to make sure you understand, not just in terms of rules of exponents, but in terms of these matrices, what's really going on here. Okay, so and this is a 4 transition matrix. Then a to the 4th squared equals a to the 8th. This is an 8 transition. A to the 8th squared equals a to the 16th. 16 transitions. Then we get a to the 32nd, then a to the 64th, then a to the 128th. So we have a 128 transition matrix in just 3 more steps. Okay, so we get quite quickly, well, what I'm getting at, what if you want to calculate the 90 transition matrix? Okay, how could you calculate the 90 transition matrix? So we can quickly get a squared, a to the 4th, a to the 8th, a to the 16th, a to the 32nd, a to the 64th, a to the 128th. Quite quickly, this means we only have to do what? 1, 2, 3, 4, 5, 6, 7 matrix calculations. Okay, then if we then want to calculate a to the 90th, find out what happens after 90 transitions. Well, in one sense, we kind of know because we can easily figure out what this matrix converges to. But it's a large matrix, it's a little harder to do that. So for 2 by 2 matrix, it's pretty straightforward. Okay, but we can calculate a to the 90th. We need only calculate what? We've got a to the 64th. Okay. Now, if we multiply a to the 64th times a to the 32nd, we get a to the 96th. Well, we only want a to the 90th, so we're not going to multiply by a to the 32nd, but we will multiply by a to the 16th. This gives us a to the 80th. Now we're trying to get to a to the 90th, so we can also multiply by a to the 8th, which only gets us up to a to the 88th power. We're not going to multiply by a to the 4th because we've got a to the 88th, and a to the 4th would give us a to the 92nd. But we do multiply by a squared. Okay. And that's only 3 matrix products. Okay, we could do that as 3 matrix products by just multiplying these two, or we can just multiply them in order. This times this. Or multiply this one times this one. That's 1. Multiply this one, that's 2. Multiply this one, that's 3. Even if we had to multiply all these out, which would give us a to the 255th, which is 1 less than a to the 256th, which would be the square of this matrix, we would only have 7 matrices to multiply, which would be only 6 matrix products. We need at most 6 matrix products to calculate any matrix and any power of A up to 255. And okay, so we can calculate A to the n. By at most, well, actually, and we have to include A, so that would be 8 matrix products. Okay, we need A because if we want to get A to the 91st power, we're going to have to multiply by A. That would be another matrix product. So we can calculate A to the n for n less than 256 by at most. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8 matrices. And we could calculate the product of all 8 matrices by 7 matrix products. I better add a word here. By at most, another 7 matrix products. We've already got 1, 2, 3, 4, 5, 6, 7 matrix products. So if we want to calculate A to the 255th, we would need these 7 products and 7 more. That's only 14 products. And that's a whole lot better than doing A times A and multiplying that by A, multiplying that by A. You need 255 matrix products. Much better to do 14 than it is to do 255. Even better, we calculate A to the n for n less than 1024 by 1. Well, you just think about it. If you square this, you get A to the 256th. You square that, you get A to the 512th. And then that's just 2 more matrix products. And then you might have to have 2 more additional matrix products here, which means how many products do you have here? You've got 7. 1, 2, 3, 4, 5, 6, 7. To get 256, you need an eighth. To get 512, you need a ninth. And then you would need at most 9 products to get any matrix up to the 1024th power. So you could calculate that for n less than 1024. Now, I'll mention something kind of important for linear algebra, for computational linear algebra. You're going to be challenged to accurately calculate the 512th power of a given matrix, especially as a large matrix, using binary arithmetic. Binary is not the same as decimal. You only get approximations. And that gets into the whole theory of the accuracy of calculations and so forth. So if you go into, say, computer engineering or electrical engineering with a computer science connection, which is what my grandson is doing in tech right now. And we'll see how that works out. He'll be okay for electrical engineering. We'll see if he gets enough computer science behind him. He's minoring in the computer science to really tackle something like this. My guess is he probably will. We'll see how much further he can go, because there's all kinds of places you can go with that. Not advocating that route unless it's one you're really interested in, or unless your calculation tells you that's best for your financial future. Lots of luck predicting that, but it's probably a good calculation at this point. Okay, anyhow, a little bit more about linear algebra and a connection in calculating large powers of large matrices. We're not going to get anywhere close to being able to really talk about that in this course, but linear algebra takes us in that direction. And you use linear algebra. You have to use theory of linear algebra to figure out how to do all this. Okay, so this, I think it's kind of neat. And really all we're talking about here is binary arithmetic. Okay, to represent any number up to 1024, you need only 9 bits. Okay, 9 zeros and ones with a sequence of 9 zeros and ones, and I'm going to kind of assume you're aware of that and know how to do binary numbers and stuff, binary decimal conversion and so forth. It's kind of a universal thing, but I expect there are a lot of universal things that people have missed. But I don't need to tell you, you're going to get it somewhere. Okay, and it's simple. It's something you can teach a 7th grader, and should teach a 7th grader. We're too busy filling them full of formulas to teach them any mathematics. Just an opinion about our curriculum. Okay, so there you have that. Okay, I'm going to stop the recording for a minute. Okay, so again, we've got matrix A, matrix B, and we want to find elementary matrix E such that EA equals B. Well, first of all, the question is, what row operation accomplishes this? Well, the row operation that gets from here to here is, and it's got to be a single row operation. Elementary matrix represents just a single row operation. There's no combination of row operations. You do combination of elementary matrices to do any sequence of row operations. We just want one row operation, and the one row operation here is, looks like these two rows got switched. So we switch rows 1 and 3. Incidentally, that's something we would never do if we're trying to do an Lu decomposition. You can't switch rows. Now, if you happen to switch them and then unswitch them, you might get away with it. But if you just got a single or an odd number of row switches, or just about any even number of row switches, you're not going to get upper triangular. Okay, well, anyhow, switch rows 1 and 3. So that does what? Well, take the identity matrix, and do this operation. You're going to get 0, 0, 1, 0, 1, 0, 1, 0, 0. You take the identity, you do the switch of the rows, and you get the elementary matrix. And that's it. EA then equals 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, multiplied by 2, 3, 0, 1, 2, 3, negative 2, negative 3, 1. And that equals what? Well, 0, 0, 1 times any column, you're just going to pick out the last number in the column. That's going to give you negative 2, negative 3, 1. 0, 1, 0 multiplied by any column is going to give you the middle number in the column. That's going to give you 1, 2, 3. And 1, 0, 0 times all this is, you've got to pick out the first number in the column. It's going to give you 2, 3, 0. That equals B. The answer to the question is this elementary matrix. There it is. Don't have an abundance of time, but I am going to just take a second to see what other error was made. There were only 2 errors made on this homework by people. There we are. So let's look at responses here. Any day now. Huh? Oh, heck. I was reading the next student. And coincidentally, there's somebody else on the same problem. So anybody that missed anything, it was in this problem. So there's going to be a little kick in yourself because the answer is really quite simple. But you have to understand the definition of an elementary matrix and recognize that what's happening between A and B is you're switching those 2 rows. Once you see that, it's easy as pie. An elementary matrix is just finding the elementary matrix that accomplishes a given operation is really very simple. Just with a little practice, it's something you're going to completely understand. And inverses of elementary matrices. That shouldn't give anybody trouble at this point. And if it does, you need a little bit of practice. Now, what's coming up is stuff that I talked about last time, so I don't have to talk about next week. I've already done it. doesn't mean it might not be a good idea, but for next week, your assignment is on Markov chains and determinants of a matrix. So go back to what we did last time, and I think what I gave you is a pretty good introduction to these things. On Tuesday, we will talk a little bit more about determinants of a matrix, because I just kind of gave you an overview last time, but I did address a lot of how to calculate a determinant. That should be pretty clear. And many of the properties of determinants, some of which you won't even see until section 3.3. I'll comment that determinants of elementary matrices are really easy. So they're either, well, and the way you use elementary matrices, the determinant of an elementary matrix is either 1 or -1. No, that's not what I said. There isn't true. Because you can add multiples of rows. So, but the determinant's always very easy. There's just a simple calculation to do any determinant. And if you can express a matrix as a product of elementary matrices, then the determinant's just the product of the determinants of the elementary matrix. And that's very simple. Okay, well, we'll go on from there. Again, I apologize for I don't know what was going on in my head there in the first half of the class. But simple elementary school errors. And I'll see you next time if there are no questions. If you got a question, pop it up. I'll be glad to answer it. Stick around. I do have another class starting. I'll have to I have to stop this thing in a couple of minutes, but glad to answer anything.